Okay, quiet. So it is a tradition that has been lasting for about 20 years that I will chair this last session, that will start with my humble words and will finish with the glory of the students that are going to finish their courses here. This year is a particular occasion because we are going to call also the students of the last 2 years, because we had suspended the seminar because of the COVID. So there will be a certain number of students. And some of them will not be here, of course, because they're busy somewhere else. But my first duty now is to introduce Professor Micheal Fardis, who is sitting there in the first row, that will give this very special keynote lecture. It's very special for several reasons. One is that I think that one of the very few items, concepts that we really believe that has been a real, true step forward in earthquake engineering is capacity design. Not many other issues have the same continuous relevance. You know, we've been using certain kind of analysis, certain other improving and so on, but capacity design is there, is a true step forward. The other reason is because of Micheal Fardis. Micheal Fardis and I met about 35 years ago. He had come back from the MIT, where I was, I think, an associate professor before coming here, but certainly did his PhD there. And he was a professor at the University of Patras. We met in the first time, I believe, in one of the commission of the CEB, which was an organization that at the time was preparing good records. And the chairman of the commission was Paolo Pinto, who has been here with us for many, many years, and now you know that he's a bit old and not that good shape, but he's certainly with us with his thoughts. So we met this long time ago. We worked together in many different projects that were aimed to produce reports, or projects that were aimed to increase the knowledge about earthquakes. And then he became the crucial person following Paolo Pinto in development of Eurocode 8. He has been for several years the chairman of Eurocode 8, so we owe him a lot for what concerns the regulations that today are used in Europe and followed in many other countries. So I will leave the stage to Micheal, but since we have many connections to remember during this afternoon, I want to show at least one slide, and I'm not sure you will recognize him. This is Micheal Fardis in 1995 in Greece, with Nigel Priestley, which has been one of the founders of the school. You see that they have in front some beer. It's very likely that the other beer is mine, but probably I was just taking the photograph at that time. We were, I believe, near Thessaloniki in northern Greece. And now, Micheal, please come, start your speech. And I'm sure it will not be that easy to recognize him anymore, but
Thank you, Micheal, but why did you do that to me? Why did you show my picture 30 years ago? It's good that my wife is not here. Thank you again. It has been a great pleasure to work with you. It has been a great pleasure and honor to work together to build let's say, the European team for earthquake engineering. Something that Micheal did not say, but I may add, is that more than 30 years ago, when we were attending a conference in the UK, and it was, we were there together with two other, let's say, rising stars in those days, of more or less the same age. One of them was, the other two were Amr Lashai and Eduardo Carvalho. And at the closing dinner of that conference, one of the old-timers, a very good friend and very well-respected expert in earthquake engineering, Jack Paucam, gave a speech. And he complained about the fact that there were these young Turks who want or aim at replacing the old guard himself, Paulo Pinto, Roy Severn, and a few more other guys. So from that point on, Michele, myself, Amr Al-Assai, and Eduardo Carvalho were the young Turks of earthquake engineering in Europe. Anyway, now both of us are looking for the new generation of young Turks. Right, Michele? Yes. Anyway, as an old-timer, I will look back to the past and give you today my view of the story of capacity design. The title is The History of Capacity Design, but my talk is more the story of how I discovered what I think now that is the story of capacity design. So I will go chronologically, starting from the point when I decided that this is a question to be solved, to the point where I discovered what seems to me right now to be the true story. So this is the reverse chronological order. I have divided my presentation into 3 parts, which I call acts. And the 3 acts have a prelude, which is a definition of what is capacity design. I'll start by quoting some official, let's say, definitions. In Euro Code 8, the current version, capacity design is defined as a process in which we try to control the seismic response by promoting ductile failure mechanisms and suppressing brittle ones using as a tool equilibrium. That is, in capacity design, one proportions the sections or parts of the structures which are considered appropriate to develop ductility for the results of the analysis, but all the rest are proportioned for action effects, load effects, which are derived not from the analysis, but from equilibrium, using as demands the resistances, the capacities of the elements which have been chosen to be detailed and designed as ductile. Now, the first definition in a code of capacity design goes back to 1975, where it appeared in the New Zealand standard, seismic design standard, which was the first time that modern day, let's say, seismic design for ductility was introduced in New Zealand. And the definition in the 1975 New Zealand standard is verbatim the same as the one appearing at in the Park and Polley 1975 book, which used to be for decades the Bible, let's say, of earthquake-resistant design of concrete structures. A slightly more expanded definition was given in the Polley and Priestley 1992 book. In both cases, let's say the New Zealand definition does not mention equilibrium as a means of establishing the demands on the brittle members and failure mechanisms, but they stress that design provides overstrength to those mechanisms compared to the analysis results, so that they don't happen first, they don't preempt the development of ductile failure mechanisms. Now, as part of this introduction, most people, when they talk about capacity design, they think of two important elements of it, what I call here signature rules. One is the derivation of shear forces in concrete beams from the moment resistances at the two ends using just equilibrium and assuming that the beam is in contraflexor. The same for column. And the second rule written at the bottom half of this slide requires the total moment resistance of beams at beam column joints to be significantly less than that of the columns framing in the same joint. The second rule aims at pushing plastic hinges into the beams and preventing them from happening in columns. The first signature rule aims at preventing shear failure in the beams or in the columns under any possible circumstances. So, what people believe in Europe right now, including myself until 2 years ago. As Michele said, in Europe, capacity design is considered the backbone of seismic design for ductility. It is considered as the way to control the seismic response and avoiding brittle failure by spreading the deformation demands throughout the structure in ductile regions. However, practitioners don't like so much capacity design because the moment it has been introduced in design, it has completely upset the design process. One cannot go anymore in a serial manner, member by member, into proportioning beams, columns, in bending and in shear, etc., by just using the analysis results and finishing and not coming back again. That's how it was done before. Now capacity design has introduced interdependence of the phases of the proportioning of design between different failure modes, shear and flexure, between different members, beams and columns, etc. So one has to go back and forth and use results of previous phases, which is very inconvenient for the designer and even more inconvenient for software developers. Now, in Europe right now, we have a broader application of the term. The so-called dissipative zones, this was the term currently used instead of ductile regions. In structures designed for earthquake resistance are not just the ductile ones. They are also the ones which are maybe less important for the integrity and stability of the wholes. For example, the horizontal elements are considered less important in that respect compared to the vertical. The elements near the top of the structure are considered less important for the whole than the foundation. And also the reasons which we choose to have the inelasticity and the ductility demand concentrated should be accessible for inspection and repair in case of an earthquake. Now, in addition to the two signature rules I mentioned before, Eurocode 8 uses capacity design in many other instances to calculate the shear stress demands in concrete beam column joints, to check or proportion the foundation and the foundation soil, to establish the moments and shears up concrete walls, to find the moments and shears in concentrically or eccentrically braced frames, except in the seismic links for the eccentrically braced ones. I'm talking, of course, of steel or composite frames. Also, the bridge decks connected to ductile piers or other elements of bridges which are required to stay elastic, as well as columns of open stories in partially infilled buildings and floor diaphragms are all designed with capacity design, the capacity design approach. Now, as Michele said, and I repeated, in Europe right now, somehow capacity design has enjoys, let's say, almost a mythical dimension in seismic design. And its very high standing is due to the introduction of capacity design as the backbone of the mother code of all European codes, including the Eurocodes, since the early 1980s. And that mother code was the CEB Model Code for Seismic Design of Concrete Structures, officially finished in 1985, but developed between 1980 and 1982-83 by a team which was chaired by Paolo Pinto and included quite a few European experts, but also some very important, the top non-European experts in seismic design of concrete structures of those days, namely Aoyama, Bertero, Jim Hirsa, and Mike Uzumeri, and Tom Boley. Tom Boley brought with him the new ideas from New Zealand and convinced everybody, especially the Europeans, to adopt the New Zealand approach to seismic design. And starting from that point, because it was Tom Poley that brought in the new ideas to Europe, there has been the opinion that he was the father of capacity design. Two examples of this conviction are shown by the quotations in this slide. One was by Hugo Bachmann, a member of the drafting team for the CB seismic code, who in his keynote lecture on capacity design presented at the European Conference of Earthquake Engineering in Vienna in 1994, said that capacity design, etc., were developed in New Zealand, mainly by Professor Poley and colleagues and collaborators. And more recently, in 2018, without naming Tom in that case, Peter Pfeiffer wrote in his Nick Ambrasi's lecture to the European Conference of Earthquake Engineering, which has been published also in the Bulletin of Earthquake Engineering in 2018, that the capacity design approach was developed in New Zealand. And he added that it might be one of the most ingenious solutions in earthquake engineering, and the structures designed by means of the capacity design approach are expected to possess adequate ductility both at the local and global level. So this is the conventional wisdom currently in Europe. How do people in New Zealand see things? A few years back, Michele mentioned to me in passing that Nigel says that it was not Tom Poley, but a practicing engineer in New Zealand who proposed and developed capacity design. And that sparked my curiosity, and later on I decided to look into this issue more closely. And this was the case when we discussed with Anil Chopra the possibility of writing a paper for earthquake engineering and structural dynamics on the history and the early history of capacity design. By the way, these early history papers appear from time to time in the journal to give information about some fundamental concepts or tools like the response spectrum, like seismic hazard analysis, etc., whose origins are often forgotten. And sometimes they lead to unexpected results. And this was one of those cases. Going back to New Zealand. New Zealand of the early 70s reminds me of a famous saying which is used in modern management theory when they want to say that a place and an environment encourages innovation through interaction, exchanges, etc. The phrase is, in Vienna, there was a sperm in the air, and it referred to Vienna of the early 20th century, Vienna of Gustav Mahler, Gustav Klimt, Egon Schiele, Sigmund Freud, etc., where almost everything in arts and sciences was happening there. And my feeling is that this was the case of New Zealand of the early 70s. I go back to Nigel. Nigel, in his introduction, to the part of the ERI's oral history series devoted to Park and Polley, parenthesis, ERI publishes from time to time interviews with very important people of earthquake engineering concerning their life and their contribution to the field. And in that case, there was an introduction by Nigel, who said that 4 people were almost equally important for the developments in New Zealand's earthquake engineering in the 1970s. Bob Park and Tom Polley, of course, but also Otto Glogau and John Hollings. And he went on to say that John Hollings was the father of capacity design. In their interviews already, Bob Park and Tom Polley, Bob Park naming John Hollings, Tom Polley not so, but talking more generally about some of our gifted consulting engineers. So both of them acknowledged that it was not them, but people in practice that proposed the concept. Of course, they went on to note their own contribution from a certain point on, but they both, like Nigel, pointed to a designer, John Hollings, as the father of capacity design. Who was John Hollings? John Hollings was a designer in a big consulting company in Wellington, who had designed many important structures in New Zealand for earthquake resistance, and who wrote in 1969 2 articles, one of them going through the concepts of capacity design and the aims in a very explicit way and giving the rationale behind them, with the support of some figures pointing to the desirable type of response of building structures to earthquake, and the other paper, the second paper, applying the concepts for the design of a real structure. So essentially, everything was there in these 2 1969 papers. However, Nigel had mentioned also another name, Otto Glogau. Otto Glogau was not a designer, and he was not named as the father of capacity design. Nevertheless, he was very, very important player in the New Zealand community of earthquake and structural engineering. He was head of the Office of Structural Design for the Ministry of Works and Development in Wellington, and under his direction, guidance, and inspiration, many government buildings in New Zealand were designed using the new concepts which were developed on the spot together with the designers of New Zealand. And they were very close with John Hollings, and they were discussing all these issues and together developing the concepts. His name does not appear directly as author of papers devoted to capacity design. One exception was a paper by Armstrong, who was one of his engineers at the office, which says, This paper indicates current thinking and outlines criteria for the capacity design of component members and joints of ductile reinforced concrete frames presently employed for public buildings in the design office of the Chief Structural Engineer, New Zealand Ministry of Works. That same paper had appeared before, co-authored with Glogau and Armstrong, apparently, in a seminar to engineers in Auckland. That was in '72. It was much later, in '75, that Park and Polley repeated these concepts in a shorter form, I would say, in their book, which was considered as the Bible of earthquake-resistant design of concrete structures. Bob Park himself, in 1993, in his paper for the volume honoring Tom Polley, the ACI Special Publication SP157, the title of Bob Park's paper was The Polley Years. Bob Park says again, well, not again, it was the first time that Bob Park said so, before even the interview to the oral history, that the beginning of capacity design was proposed by Hollings. More details were given later by two other people who were around those days in New Zealand. One of them is Les Megget, who is still, as far as I know, around. He's teaching at the University of Auckland. He did a master's with Bob Park in '71, and he was editor of the New Zealand Bulletin for the Society of Earthquake Engineering for a long time, especially at its early years. And in this long citation, which appears on this slide, he gives a summary of the very influential papers of John Hollings concerning capacity design, and he also names John Hollings as the father of capacity design. The second practice engineer who again confirmed the role of John Hollings was Latham Andrews, who was president of the New Zealand Society of Earthquake Engineering for 2 years, editor of its bulletins for longer, and also acknowledged by Park and Polley alongside Hollings and others for constructive comments and discussions in their book. Let me repeat some of the part of the quotation by Andrews, because it gives a feeling of the importance that New Zealanders gave to the contribution of John Hollings. The paper by Andrews, which goes through the history of the Society of Earthquake Engineering in New Zealand, says that the decade of the 1960s were marked by two events. The first was the discovery by Nathan Newmark, maybe the most important person in earthquake engineering ever, that the elastic analysis significantly overestimates the demands in concrete frames and concrete structures under recorded motions, and that realization led to the introduction of the force reduction factor, what is called behavior factor in seismic design. So, Andrews says that the proposal for capacity design by Hollings at the end of the decade was as important as the concept of the force reduction factor introduced by Newmark. So, this is the end of the New Zealand part of the story, which concludes with the realization that those in New Zealand who appear to know consider John Hollings as the father of capacity design. However, when I reached the same conclusion sometime in 2017 in my search for the origins of capacity design, almost by chance, it was brought to my attention that the two signature rules of capacity design had appeared already in 1961 in the book by Bloom, Newmark and Cornings, published by PCA concerning seismic design of multi-story buildings. And they had also appeared in the CAO recommendations of the early 70s or even before that. And somehow, in small print, both John Hollings and Park and Polley recognize this. John Hollings says, Bloom, Newmark and Corning and the CAO code give rules for designing the shear capacity of beams based on the assumption that the hitch forms at each end of the beam. That's signature rule 1. And Park and Polley, in a paper which was published before their book, say that the ACI code of 1971 essentially is based on the philosophy that themselves were proposing as capacity design, and that philosophy and these provisions in the ACI code were based on the 1967 and 68 editions of the CAO code. So, apparently, the elements for capacity design pre-existed. Pre-existed in the 1961 Bloom, Newmark and Corning book, which was a very important book, but unfortunately was very soon forgotten. Maybe because it has not been published by a major publisher like Wiley, McGraw-Hill, etc., but just by PCA, the Portland Cement Association. And there, the figure that you see here, which is signature rule 1 concerning the derivation of the shear force in beams from the moment resistances of the end sections appears. Along with a very lengthy application of the strong column weak beam concept in an example which does not employ what we call now capacity design of columns in bending, but provides overstrength to columns compared to the beams so that the plastic hinges form in the beams. So essentially everything was there. Now, what was behind that book? It appears that the chapters where these rules appeared were contributed by Nate Newmark. But Mette Sozen, then a very young junior faculty at the University of Illinois at Urbana-Champaign, was preparing drafts of those chapters for Newmark, and Newmark was going through them, correcting them, and then they were published under his name. Mete just appeared as the first name in the acknowledgements of the book. But apparently, he was the one who contributed this work. And in personal communication and in an interview that we will soon see, he says that the signature rule for shear in beams was developed by himself, essentially. He doesn't say so, but it's clear. For pre-stressed concrete beams in bridges, which was the field where Mette Sosen specialized before focusing on earthquake engineering. As late as 2018, Mette Sosen, in his own interview to Bob Reitherman for the ERI's Oral History series, is asked the question of his role for this book. And he says that those ideas were present there and that he prepared drafts of the chapters where these ideas appeared. And he also adds that these rules, at least the one for shear, come from bridge design. He goes on to say that essentially he disapproves of the term capacity design, which is never used in the States. He would have preferred a different term, but he does not see a need for a term for these rules. But he points out also that the method was called capacity design and adopted by engineers in New Zealand who were also successful in convincing European engineers to use it. This is the latest piece of information that I have, confirmed by the CAOC recommendations themselves. The oldest copy of the CAOC recommendations I have in my library dates from 1973, but apparently these rules were there before 1973. And I have a copy of those rules from the CAOC recommendations, and they are there. Conclusion. Apparently, the rules come from Mette Sosen, at least the most important elements of capacity design come from Mette Sosen and nothing numerous. What has been contributed by whom, how much was due to Mette and how much was due to Newmark, I don't know, and I'm not sure that anybody will ever know. And second, these rules were soon adopted in American codes and led John Hollings and other New Zealand practitioners to build on them what they called capacity design as a design philosophy. Then Tom Poley brought these ideas to Europe and was instrumental in their incorporation in European codes. So this is what I understand now for the story. Unfortunately, all players are not with us anymore. And there are some details which will never be revealed. That is, there is no publication before the 1961 book by Bloom, Newmark, and Corning with Mette Sosen's name and what has been included in that book. But I trust that what he says in his interview and what he's told me in some private, let's say, exchanges, fortunately a few months before he passed away. So I trust that this, what he said is true. So this is the end of the story as far as I know it. And with the end of my presentation, I want to thank very much some people, starting with Michele, whose initial remark concerning what Nigel told him sparked my interest in looking into the issue. Second, to Bob Reitherman, Les Meggett, and Mette Sozen for providing first-hand information and also commenting on the drafts of the paper I prepared for earthquake engineering and structural dynamics. Third, to Peter Pfeiffer, because it was through Peter Pfeiffer that Mette signaled, let's say, his, I would not say objection, but his questions concerning our belief that everything was done in New Zealand. And also, thanks to Anil Chopra for encouraging me to write that paper and for commenting on his draft. So, this is the end of my story concerning this story. And with that, I also thank you very much, you, for listening to this maybe boring story, which may be of interest only to old people like myself. Thank you so much.
Michael, thank you for playing Hercule Poirot in this Agatha Christie story. But more than that, I think that this presentation has been very important because it has shown us a lot of relevant issues, not related to capacity design, that everybody here, with few exceptions, these people in the first row, for example, know very well capacity design. But the point is, how many things are already there? How many things we can find simply studying and reading and being acquainted to the giants of the past. And this is something that we should do all the time. Too often, too many times, it happens that someone believes that he comes out with a new revolutionary idea, which is not revolutionary at all. And I think that this is fundamental for any age, but particularly for young people, and this seminar is always oriented to young people. So we do not have the tradition of asking questions or expressing comments after a keynote lecture. But because of the subject, if there is anyone here who wants to say something, who wants to say, no, it was Tom Pauley, or because he knows very well these kind of things, I decide that it is possible to express comments. If not, we go to the next part of today. So, anyone wants to say something? No? Okay, Michael, then we thank you again. Thank you again for being here, for being a friend of many people here for so many years. And I hope really that we will continue working together. I hope that we will go back to the meeting in Santorini like 30 years ago when there was that Greek rich man who was giving us that magnificent place on the top of the island. So let's hope to have a long future in front of us.
twice or 10 times because I'm a few years older than you, and I very much want to stay with the community and contribute to it for a few more years. Thank you.
So guys,